Yes. Hello, I'm Benjamin Quiring, along with my co-authors. John Reppy is here in the audience. Olin Shivers couldn't make it. And this is analyzing binding extent in 3CPS. So 3CPS is a new optimizing compiler talk, or a new optimizing compiler project, and we have a slogan, which is that if the clicker would go, perhaps not. Well, great. We are the anti-MLton. So what do we mean by this? Clearly, we're being, not completely serious. So MLton, for those of you who don't know, is a whole program standard ML compiler that produces extremely high performance executables. It's very good. And the way that it does this is it first performs a higher order flow analysis on the program. It uses the results of that flow analysis to perform monomorphization and defunctionalization. And then at that point, it's able to apply classical compiler analyses and optimizations, such as classic data flow analysis. And so to us, MLton sort of stands as the best, very high performance. And we'd like to qualify that by saying so far. But it's so good that we feel that the only way to do better is to take a radically different approach to compilation. So our approach is to maintain a higher order polymorphic IR throughout compilation. So we'd like to retain the flexibility of this IR, which allows us to do separate compilation and monomorphizable type features like general algebraic data types. But we'd also like to stay performant while we do this. And the way that we are going to do this is by optimizing the functional part of the language. So we're trying to target lambda and environments, which are the things that are unique to the higher order IR. And the way that we do this is we're going to try to understand the dynamic lifetime of environment structure. So what is environment structure? Well, environment structure is not data structure. There's been heaps of work on lists and arrays and all of these things. These are data structures. Environment structure is the machinery and the operations associated with implementing bindings, scopes, and lambdas. And this is really the operations that glues together the program. And so higher order languages are all about environments, so let's target environments. So let me describe sort of a simple example here. I've defined this function named adder, which takes a parameter x. It defines an inner function, which takes a parameter y, and it sums them. And then we're going to immediately consume that closure over adder. So if we think about what's going on at runtime, when we enter the adder function, we're going to push a stack frame. We're going to take that variable x, and we're going to make a binding for x on that stack frame. Next, we're going to go and create the closure. And the first step of creating the closure is noting that this inner function captures x. And sort of the default implementation for compilers is to take the binding of x and copy it into the heap. Then we'd finish creating the closure by having the closure point to this record that's in the heap. And so the clear optimization is don't copy the thing into the heap, right? Now, the problem comes is when we change adder a little bit. Now we're going to make it truly just like a curried version of add. We're going to return that inner closure. And so the problem now is after we return that closure, we have to pop our stack frame. And so the binding of x is now kind of destroyed, and this closure is what is it referring to? So in particular, what happens if later on in the computation the closure looked up x? Well, clearly the not the right thing would happen. And so the main problem here is that the lifetime of the binding for x is longer than the lifetime of the stack frame itself. So this brings us to talking about lifetimes or extents. So the big idea is that we define a taxonomy of 3 extents, which is where the 3 in 3CPS comes from in our project name. And these extents are going to map naturally onto the machine resources used to implement variable bindings. So the idea is in the compiler, we have some analysis or something that's going to collect a set of facts about each variable. What extents do these variables have? And then later on in compilation, we can make a decision based on those facts about how to actually implement the binding. So our particular taxonomy of extent is heap, stack, and register. And I hope you can see why these clearly map onto machine resources. The heap goes to the heap, the stack goes to the stack, and register would go either into the register set, or if you pre-allocated a sort of a static block of memory at the beginning of computation. So let me go into these in a little bit more detail. Heap extent describes lifetime of any length. There are no constraints it places on lifetimes. And so heap extent essentially represents a fallback in terms of implementing variable bindings. Since it's the most heavyweight machine resource, we'd like to move things out of the heap. And so a simple syntactic approximation for, when can you implement something on the heap is you can always implement things on the heap, but sometimes you have to. So if we consider that binding for X earlier, for matter, that binding has a very long lifetime potentially, and so we kind of have to, put it in the heap. Our second extent is stack extent, and this describes a lifetime when the binding's lifetime is shorter than the lifetime of the stack frame that closes over it. And so, in other words, that binding should not be referenceable after we pop the stack frame. And so a good syntactic approximation, which is used, by compilers to date, is that if a variable X does not have a free reference to it in any lambda, then you can actually implement that on the stack. And so here's a favorite example of compiler writers. We have factorial. Factorial takes a parameter n. It's going to do a recursive call at some point, and then after it does the recursive call, it needs to come back and do a multiply. So we're not doing any sort of accumulator sort of tricks. And so n here is clearly not closed over by any lambdas, and so it can definitely put on the stack. But in some sense, we need to put it on the stack, because if we think about it, we have to have multiple instances of n alive at any one time. Our final extent is called register extent, which describes a lifetime where the bindings for some variable X does not exceed the creation time of the next binding for X. So in particular, that parameter n in factorial does not have register extent because those lifetimes intersect. When we have n equals 10 on the stack, we also need n equals 9, and we can't get rid of that binding for n equals 10. So both of them need to be alive at the same time. And so in other words, register extent says that at most one live binding for X can be there at any one time. And so there's this, once again, a syntactic approximation which modern or compilers to date use, which is that you can't have a free reference to X from any lambda, and you can't have any function calls between the definition of the variable and all of the uses. And this basically means that you can't have a recursive call that loops around and binds the variable when you still need to use it. And so the sort of story of this paper is we can do better than these syntactic approximations. Well, I would hope so. And it turns out that we can do a whole lot better. So I'm going to show some numbers here. Don't be too scared. We have this program, Nucleic. It's a standard sort of compiler benchmark. The number of variables in this program is 7,800. That's including naming all of the intermediate temporaries in the compiler. And if we use the syntactic approximation, 88 of these would be needed to sort of be left on the heap. And so, as I said a little bit earlier, what the compiler is going to do is run our analysis, and then it's going to see how many of those it can move off the heap into the stack or onto the registers. And so it turns out that our analysis moves 86 out of those 88 off of the heap and into the stack, 97.7 of them. And this isn't just a one-off thing. We have a whole bunch more benchmarks where we move high 90s or high 80s percents of variables off of the stack, which is really quite impressive. There are a few standalone examples. For example, the CPS conversion that gets a lower ratio, and that's mostly because it creates lots of closures which live for a long time, and that really forces a lot of bindings to also live for a long time. Something that I'd like to note is that this analysis that we have is not exponential time or something. It runs quite quickly, even though it's a research implementation. It's very scalable. So something that I've presented was, we're able to remark variables. But how do we know that the dynamic behavior actually matches, what I'm telling you? And I think this is important to note because we don't have a full compiler implementation yet. This is sort of the first technical result of the project, and we're getting there. However, I can tell you that the dynamic numbers do match, because what I've done is I've programmed an instrumented interpreter that can basically run, a concrete version of the analysis. And what we find is there is a correlation between us promoting things out of the heap and actually moving bindings out of the heap itself. And this also holds for the stack. There's something else we can do with this instrumented interpreter, which is that we can actually show that the analysis is quite precise, despite being something similar to zero CFA. So the idea is that I can run the interpreter on a single execution trace, and that will collect some facts for me, like that X is a register, X has stack extent, Y has register extent, and Z has register extent. And I can also run our analysis, which is going to give us a subset of those facts, since it's a sound approximation. Then we can think of this as squeezing the ground truth, which is sort of the intersection of these facts across all traces. It's squeezed between these numbers. And what we find is that the single trace and the analysis are super close in practice. And so, if you wanted to do one CFA, something a lot more clever, more precise, it's actually not going to buy you a whole lot. And that doing this simple, easy, quick thing is getting you almost all of the benefit. So how do we do this? We programmed a new higher order static analysis based on abstract interpretation. It's going to model the stack behavior of the abstract machine. And we need to tell if things are live. And so what it does is it does kind of like this little abstract garbage collection. And the idea is as you're stepping the program along in the abstract interpretation, we're going to look for events that say, this thing cannot have this extent. So there are two types of events, one for stack and one for register. For stack, we're going to inspect every single pop that happens in the abstract machine. And so if we have some binding X that's still alive, but the frame associated with X is being popped, that means X cannot have stack extent. For register extent, we're going to inspect every single bind that we have for variables. So if we're binding a variable X, if there's still a live occurrence of it out there, then X cannot have register extent. So unfortunately, due to time constraints, I can't actually, show you a bunch of equations, and I'm not sure you would want to see them anyways. So that's in the paper, if you're interested. What I also haven't talked about is the whole, CPS, part of 3 CPS, and that's also in the paper. So we have this formalism in something called factored CPS, where user things are user things, like lists and arrays, and continuation things are, their own thing. And this was originally introduced in the Orbit compiler. We also have a stack protocol for this CPS, an abstract machine that actually uses that stack to push and pop. And we have multiple continuation arguments, which means that we can have long jump returns. So if you're raising an exception, just pop some number of stack frames. You don't care how many. And this somewhat complicates the analysis and is kind of a cool result. And this was inspired based off of Dimitris Vardoulakis's CFA2 work. So in conclusion, we are a new compilers project, 3 CPS, an environment-centric approach to compiling functional languages. The new idea is to categorize extent to optimize environment structure, and our extents are heap, stack, and register. We have a new analysis, which is an abstract interpretation that identifies binding extent, and this is scalable. It's like 0 CFA. It's executable, so one of our artifacts is the current compiler implementation, and it's correct. I've also introduced mechanized proofs, which are part of the artifacts. Finally, we have some supporting numbers, both static and dynamic. So what we show is that a significant number of variable bindings can be moved out of the heap, both just looking at the syntax and looking at the dynamic behavior of the program, and that it's hard for this analysis to do better. It's really quite precise already. That's the end of my talk. Any questions? Thank you.